This is Mr. B. Giriraju, Professor of EC Department, ACE Engineering College, Hyderabad. So in the last video, I have completed Unit 1. So today I will start Unit 2, Signal Analyzers. So before going to start Unit 2, once again I will recall topics in Unit 1. So actually Unit 1 having topics as first one, block diagram of measuring system, and the second one, performance characteristics of the measuring system. Actually this having two characteristics. First one as the static characteristics, and second one dynamic characteristics. So with the help of these two characteristics you can measure system performances. Actually your static characteristics are the memoryless type of characteristics, and dynamic characteristics are the memory type of characteristics. So with the help of these characteristics you can study so types of errors like that. Actually in this unit we are having errors as three types: gross errors, instrumental errors, and random errors. The gross errors are the human mistakes, and systematic errors are the instrumental errors. Random errors occurs due to the reason of noise. To identify this type of noise, we have to take help of the statistical approaches. So with the help of these approaches you can identify and avoid random errors. So now we have to start measuring instruments. So actually your measuring instrument you have to study with the help of directional moment. So actually here we can find instruments, measuring instruments as DC voltmeter, DC ammeter, AC voltmeter, ohmmeter, two responding RMS voltmeter, multimeter, so like that. So with the help of these topics you can understand Unit 1. So now I will start Unit 2, signal analyzers. So actually this unit having so topics as wave analyzer, frequency select wave analyzer, heterodyne wave analyzer, distortion analyzer, and methods to measure harmonic distortion, power analyzer, capacitive voltage analyzer, spectrum analyzer, logical analyzer. So these topics are belonging to wave analyzer. So second part as a signal analyzer. So actually this having topics as fixed and variable frequency oscillator, basic sine wave generator, sine and square wave generator, square and sine wave generator, function generator, sweep frequency generator, arbitrary wave generator, zero pattern generator. So these are the topics in Unit 2. So now I will start from wave analyzer. So actually wave analyzer is a harmonic distortion analyzer. Means the total harmonic content in a waveform, any complex waveform, is made up of fundamental and its harmonics. Actually here any wave is the combination of the some harmonics that having some amplitude and time frequency also. So wave analyzer is used to measure the amplitude of each harmonic or fundamental frequency individually. So wave analyzers generally you can refer as frequency selective voltmeters, carrier frequency voltmeters, and selective level voltmeters. So the instrument is tuned to frequency of one component whose amplitude is measured. Some wave analyzers have the automatic frequency control which tunes to the signal automatically. So actually here this is the circuit diagram of wave analyzer. So actually here we can classify the wave analyzers as two types. So one is the frequency selective wave analyzer and another one is the heterodyne wave analyzer. So your frequency selective wave analyzer operate the frequency 20 Hz to 20 kHz. Heterodyne wave analyzer 10 kHz to 18 MHz. So this is the basic block, basic circuit diagram of the wave analyzer. So actually this wave analyzer consists of a primary detector. This is the primary detector and a rectifier. So actually your primary detector is formed a simple LC circuit. It allows only one particular frequency to which it is tuned and rejects all other frequencies to pass rectifier and the output device. The output device is nothing but DC voltmeter. This part is the DC voltmeter. So which is calibrated to indicate the peak value of applied input signal sinusoidal wave. So actually a rectifier, so this part used to achieve the average value of the applied AC input voltage, input signal. So actually applications of wave analyzer are electrical measurements, sound measurements, vibration measurements. So with the help of wave analyzer, you can measure electrical measurements. You can measure sound measurements. In the same way, you can measure vibration. So these are the applications. So actually here we have classified wave analyzers as two types. One is the frequency selective wave analyzer and other one is the heterodyne wave analyzer. Now I will explain frequency selective wave analyzer. So this is the basic block diagram for frequency selective wave analyzer. So this type of wave analyzer using for the purpose of measure the frequencies of audible range 20 Hz to 20 kHz. So actually this having blocks as first one input attenuator. So this analyzer consists of a very narrow passband filter tuned to a particular frequency component according to requirement. So this figure shows the block diagram of frequency selective analyzer. So the complex waveform is fed to the input. to attenuator. So actually here this attenuator allows large number of signal amplitudes to the selective amplifier. The output of the attenuator applied to high Q active filter. Actually this is also one of the low pass filter. So through a driver amplifier. So here IQ active filter, this will work as a low pass filter. So this contain RC resonant circuit and filter amplifiers. So connected in cascade form. This allows the selected frequency to pass and rejects the other remaining frequencies. So the final amplifier supplies the selected frequency. That means here output of the high Q filter so is a selected frequency signal to the meter. So you can observe here this is the meter. So which indicates the magnitude of selected frequency, and the output buffer amplifier which is employed to derive the electronic counter. This analyzer is also known as frequency selective voltmeter. So this analyzer should have low input distortion. So actually with the help of this analyzer, so you can measure frequencies audible range from 20 Hz to 20 kHz. So this is the explanation for frequency selective wave analyzer. So next one, heterodyne wave analyzer. This type of wave analyzer used to measure frequencies in RF range and also ranges above 20 kHz to 18 MHz. So already we have mentioned here. (20 kHz to 18 MHz). So actually this is the basic block diagram for heterodyne wave analyzer. So this is having first block as attenuator. So actually here heterodyne means this is the mixing process. That means the operation depends on the principle of heterodyne or mixing. So the input to be analyzed is applied through a attenuator. So and untuned amplifier before being heterodyned in mixer 1. So to a higher IF range with internal local oscillator. The output of this local oscillator is varied and adjusted to obtain constant frequency such that the frequency should be in pass band of IF amplifier. The output of mixer 1 is an IF signal. This is amplified by 30 MHz of IF amplifier. The output of the IF amplifier is again heterodyne with a 30 MHz signal coming from a crystal oscillator, coming from a crystal oscillator. Due to this, output of mixer 2 is centered on a zero frequency. So the active filter is adjustable band width and symmetrical slopes allows the selected component. So amplifier and a detector whose output can be read by a decibel calibrated scale. So this meter is also referred heterodyning tuned voltmeter, operates in the range of 10 kHz to 18 MHz. So this is the function of the heterodyne wave analyzer. That means now here, so you have to mixing signals with the help of mixer 1 and mixer 2. So finally this will operate in the range of 10 kHz to 18 MHz. So this is the heterodyne wave analyzer. So now I have given some idea about the wave analyzer. So here we have classified as two. First one as frequency selective wave analyzer and second one the heterodyne wave analyzer. So now I am going to explain distortion analyzer. So actually here everyone knows idea about the distortion. Distortion means the alteration of the original shape of a waveform. That means suppose sine wave. So due to some reasons, so we got some problem. That means that problem we can identify in the amplitude. So in that case, so you can say that waveform having some distortion. So that's why you can define distortion, the alteration of the original shape of waveform. So function of distortion analyzer, measuring the extent of distortion. So that means the output differs from the waveform at the input, introduced by a active or passive devices. So already everyone knows about the active or passive devices. Active devices are the combination of the voltage, current and diode, so like that. And the passive devices are the combination of the RLC components. So an amplitude distorted sine wave is made up of pure sine wave components, including the fundamental frequency f of the input signal and harmonic multiply frequency 2f, 3f, 4f, 4f, etc. So harmonic distortion can be measured accurately using harmonic distortion analyzer. So generally this is called the distortion analyzer. The total harmonic distortion is given by under root of summation of harmonics RMS whole square divided by fundamental RMS. So now with the help of distortion analyzer we can measure total harmonic distortion, so also be written as THD equal to under root of E2 square plus E3 square plus so on E square n divided by F, where TH is the total harmonic distortion. So EF is the amplitude of fundamental frequency including the harmonics. Here E2, E3, En are the amplitude of the individual harmonics, because of every amplitude having some, every harmonic having some amplitude. That's the reason. So you have written here E2, E3, so on, are the amplitude of individual harmonics. So I will give one example. Compute the THD of a signal that contain a fundamental signal of Vt equal to 100 VRMS, harmonics E2 equal to 3 VRMS, E3 1.5 VRMS, and E4 0.6 VRMS. Here we have taken only 3 harmonics and EF equal to 10 VRMS. So already you know the total harmonic distortion is under root of E2 square plus E3 square plus so on E square n divided by EF. So already here given E2, E3, E4 are the values, substitute here. Already you know the value of EF, substitute here, then you will get 34.07%. This is the percentage of total harmonic distortion. So methods to measure harmonic distortion. So generally here we are using to find harmonic distortion in 3 methods. First one is the resonance bridge method, second Wein's bridge method, and BGT network method. So actually, so this is the circuit diagram for resonance bridge method. So to explain this method, we are taking help of the bridge circuit. So this is having components as resistances and inductance, capacitance, and one detector. So now you have to provide some test wave to bridge. So actually this is the balanced, this bridge is balanced for the fundamental frequency. So that means this having LC tuned to the fundamental frequency. That means this having some LC circuit. With the help of LC, we can tune the fundamental frequency. Now the bridge is unbalanced for the harmonics. So if the fundamental frequency is changed, the bridge must be balanced. Actually, so according to our bridge network theorems, so you must have to balance the bridge position. So that means you should write bridge balance condition as R1, R2, R1, R3 is equal to R2 plus R4. So this is the bridge balancing condition. So with the help of changing values of R1, R3 and R2, R4, so you can balance the bridge condition. So now here also you have to do like that. So that's why now you have to tune components LC. So in that case automatically the circuit will be balanced. If L and C are fixed components, then this method is suitable only when the test wave has a fixed frequency. So when a continuous adjustment of the fundamental frequency is desired, so in that case better to go for Wein's bridge arrangement. So that is the next one. So second method, Wein's bridge method. So actually is also one of the method to find harmonic distortion. So here this is the circuit diagram for the Wein's bridge circuit. So bridge is balanced for the fundamental frequency. The fundamental energy is dissipated in the bridge circuit. So here also this having components in the form of RLC. That means is also one of the passive device. So with the help of this circuit, so now you can balance the fundamental frequencies. So now you have to find harmonic distortion for the test wave. So only the harmonic components reach the output terminals. The harmonic distortion output can be measured with a meter. So now for the balance capacitance values and resistance values, you should maintain capacitance values C1, C2 is equal to C, and R1, R2 equal to R, and R3 is equal to, so that is 2R. So in this case, definitely you can balance the fundamental frequency. So this is the idea about Wien-Bridge method. So last one, third one, BGT network method. So in the BGT network method, so this is the circuit diagram. So the input inductor L and capacitors C, so are tuned to the level of the fundamental frequency. Because of this will act as some tank circuit. So that means you can call as tuning circuit. So now with the help of values L and C, you can tune the level of fundamental frequency. So whereas the resistance R is varied bypass the fundamental frequency signals, since the tank circuit and then bypass through the resistor. So therefore, any harmonic signal reach the output leads, and this distorted output is indicated by an output meter. So actually at the end of these terminals, you will get some harmonic distorted output. So these are the methods to find harmonic distortion. Simply you can call as these are the harmonic distortion analysis. So next I am going to explain power analyzer. So actually your power analyzers, particularly using particularly for the purpose of modern industrial applications. So in modern industrial electronics, so you have to monitoring power stages. So you have to maintain and systems also. Due to this, it is observed that the input connected to the every device may not be a clear steady sinusoidal wave formed with constant amplitude. That means you should maintain clear signal without any disturbance. That means you have to provide clear input to supply to systems to get better results. Hence, devices are not working properly. Every time check the quality of the input power. But practically load connected to AC line and power distribution both contribute to a power problem. So now here with the help of power analyzer evaluate the power problems and also provide complete documentation to the test performed. So that means now with the help of power analyzer, every time you can monitor the input supply and you can observe changes in the output. So here, this is the block diagram of the power analyzer. So this is a 3-phase 4-way system of supply. So you can observe here. So the currents in each line and line voltages are sensed with the help of sensing elements. So we can observe here R, Y, B, these are the power supplies, and we have some voltage monitoring values and current monitoring values. So here the sensed currents and voltages are selected sequentially by multiplexer. So observe here, this is the multiplexer. Output of the multiplexer convert into digital form and that provide to microcontroller and a display. So with the help of keyboard you can control the microcontroller. So finally you will get some series line voltage. So this is the block diagram of power multiplexer. So here the multiplexer combines all the above signal into a single channel. The output of the mux is connected to analog to digital converter. The quality signals get converted to digital signal which is given to the microcontroller. So according to the program stored in memory of microcontroller, computations and the calculations are done. Finally, the calculated quantities are displayed using the display. So unit. So with the help of display unit, you can observe output of the every sensing element, whatever you want. So that value you can monitor with the help of display system. So applications of the power analyzer: product development, troubleshooting areas of power distribution, to monitor power and operation of the device malfunctioning, to indicate the problem caused using record event. So these are the applications of the power analyzers. So next topic, capacitance voltage analyzer. So here capacitance voltage analyzers measure and give capacitance versus voltage and voltage versus capacitance, capacitance versus time, and actually these are the characteristic of semiconductor devices. Generally can observe capacitance voltage analyzers measures and give the combination of the capacitance versus voltage and capacitance versus time. So actually here capacitance voltage results are highly correlated with performance parameters of functional devices such as FET, memory cells, charging, coupled devices, and isolation structures. So the instrument provides 0.1 femtofarads, 0.1 into 10 to the power of -8 typical sensitive TP test small devices, ranges up to 20 microfarads at 100 kilohertz to test large lags or forward biased devices. So here measurement of 1 to 100 readings per second can be selected, speed resolution, trade-off and optimized. Correction can be made for transmission line errors because of connections. So second one, current capacitance versus voltage and capacitance versus time data are used to determine the important characteristics such as semiconductor doping profile, threshold voltage, oxidized characteristics, mobile ion density, and minority carrier lifetime. The internal voltage source can supply up to 50 milliamps from minus 20 volts to plus 20 volts with a 5 millivolts resolution. The voltage can be applied in the form of a DC, staircase, dual staircase and pulse form. So actually there is a provision to apply up to 200 volts using an external source. The sensitivity for capacitance is typically 0.1 femtofarads. So 0.1 into 10 to the power of minus 15 farads. So second one, the sensitivity for capacitor for time parameter is typically 0.1 mF, and the measurement range of capacitance is typically 20 nanofarads. So these are the idea about capacitance, voltage analyzer. So next I am going to explain spectrum analyzer. So actually here this is the very important analyzer to find amplitude, frequency, so voltage and current values in a different manner. So already you know the idea about oscilloscope. So with the help of oscilloscope, you can measure values of amplitude, frequency, voltage, time, so like that. So actually here spectrum analyzer, an oscilloscope to display signals with time. As the x-axis, it is in time domain. It is also useful to display signals in the frequency domain. The instrument provides this frequency domain U is called the spectrum analyzer. Spectrum analyzer provides a calibrated graphical display on its CRT. So with frequency on the horizontal axis and amplitude on the verification. So that means here, so you can observe output waveforms in the single line. So like this. That means this will express higher only amplitude of the time. That means amplitude will express in the form of amplitude with the help of amplitude and frequency levels. A spectral analyzer provides calibrated graphical display on the CRT. So with frequency on the horizontal axis and amplitude on the verification. So spectrum analyzer provides a display of the frequency spectrum over a given frequency band. Spectrum analyzer use either a parallel filter bank or a swept frequency. Swept frequency, so like this. So actually this is the filter bank analyzer. So spectrum analyzer use either a parallel filter bank or a swept frequency technique. So in a parallel filter bank analyzer, the frequencies range is covered by a series filters. whose central frequency and bandwidth are selected that they overlap each other as shown in this figure. So actually this is the parallel filter bank analyzer. So this will provide output in the combination of amplitude and frequency. So like this, actually this is having unparalleled filters. So you will get overlapping outputs are like this. So typically an audio analyzer will have 32 of these filters, each covered 1/3 of an octave. So for wideband narrow resolution analysis, particularly at radio frequency or micro signals, the swept technique is preferred.